Okay, hello. We are going to start chapter 5 about binomial distribution. So this chapter is quite different from the first 4 chapters. So in the sense that in the first 4 chapters, there was no model. It was just summary, description, and just calculation, right? Calculating probability, calculating conditional probability, mean, median, variance, range, these kind of measures. Those were just kind of summarizing and describing data. But in this chapter and the next chapter, we are going to study a scientific model. In a scientific model, we usually make assumptions. So our goal is to simplify the phenomena we are experiencing. We would like to explain what we observe in a simpler way. That is science, right? To do that, we need assumptions. We are going to do the same thing in this chapter. So think about this. In the first 2 chapters, we learned probability. So probability is a complete way to describe the data. The distribution of the data is perfectly described by probability distribution table. So if the number of possible outcomes was small, then it's not a problem. But in practice, the actual number of possible outcomes is quite a lot. So probability distribution table is not practical. So we cannot show all the table like for all the possible outcomes, right? Meanwhile, maybe then when the distribution becomes more complicated, you can summarize them with mean and variance. There are summary measures. Then the problem is they are simple and they are a compact summary of the data, but as I said, they lose information. They are not a perfect measure. So they are in the process of summarizing the data information, they miss some of the important aspects, right? So then in this chapter, we are going to change our approach. What we are going to do is we are going to make assumptions. Some key property or key feature of the experiment will be incorporated as an assumption, and then based on the assumption, we can summarize the data without losing any information. And so we are going to call that parameters. So under a model, under a set of assumptions, we can describe the entire distribution with just a few number of parameters. That is what we are going to do. So far we have considered 3 different approaches. Like probability is a perfect, complete description, but it was not practical. Mean and variance, some summary measures, descriptive measures, were compact, but it loses information. And the third approach here is we are going to make assumptions. Under the assumptions, we don't lose any information, but still we can summarize the data with a few numbers. That's what we are going to do here. So far, we have not used any models. Okay. And in statistics, there are a lot of probability models, a lot of distributions, right? However, we are going to study only 2 typical and most common and important types of distributions. In this chapter, we are going to learn binomial distribution, and in the next chapter, we are going to study the normal distribution. So there are more distributions like Poisson distribution, exponential distribution, gamma distribution, beta distribution. There are a lot of distributions, but I'm not going to discuss them in this course. So, okay, let's get started. We are going to start the binomial distribution. So relevant chapters. So here I'm showing you 5 examples, and you find one random variable that is different from the others. So A, outcome from a coin toss. B, gender of a randomly chosen person. C, whether a randomly chosen student has a passing grade in calculus or not. D, price of a randomly chosen dish on a restaurant menu. And E, answer to a true-false question in an exam, right? So think about the similarities and differences among these random variables. It's just brainstorming. The answer is D. So price of a dish is like a number. It's a, it is a real number, positive number. But all the other random variables have yes or no structure. Outcome from a coin toss can be either heads or tails. Gender can be either man and woman. And a student has a passing grade, pass or fail. Answer to true-false question is either true or false. So all the other four random variables have yes or no type binary outcomes. There are only two possible outcomes. We call that binary, right? A random variable is binary if there are only two possible outcomes. As you just saw, there are different examples: man, woman, win or lose, positive or negative, yes, no, true, false. You can think about a lot of examples, but in this chapter, we are going to label them success and failure. Right? So heads could be success or tails could be failure, but also you may treat tails as success and heads as failure. It doesn't matter. I'm not saying so. Even though I say success and failure, but they are value neutral. I'm not saying success is good and failure is bad. I'm just choosing. It is just a tradition, right? In statistics. And numerically, when we need a numerical description, I'm going to write success as 1 and failure as 0. So binary, 1 or 0. By the way, here you may wonder why it should be 1 and 0. You may use 1 or 2, 1 and 2, or 1 and minus 1. That is possible. But I will stick to this 1 and 0 and 1 labeling, encoding, because by using 0 and 1, there are a lot of nice mathematical properties. So, 0 and 1 are two most important numbers in mathematics. So by using them, we obtain many nice properties. So I'm going to use them. So I wrote down some examples, pretty obvious. But again, I said you may treat like either as 1 or 0. So you can encode man as 1 or woman as 1. It doesn't matter. It does not matter. Just that's your choice. And depending on the context and depending on your interest, you can switch the encoding. That is not a problem. Okay, so that's it. That is basically the only assumption we make. So like from now on, we are going to maintain that assumption. The assumption is that there are only two possible outcomes, 1 and 0. So call them 1 and 0 is not an assumption. The only assumption is two possible outcomes. And under this assumption, we can obtain many nice properties, right? So there are two possible outcomes. That means there are only two probabilities. If you know these two probabilities, you know everything about the distribution. And these two probabilities can be actually summarized into one number. That is usually parameterized in this way. We are going to parameterize the probability of success, probability of 1, as an unknown parameter p. Then, if you have parameter p, then automatically the probability of failure, or the probability of 0, should be 1 minus p, because there are only two probabilities and sum of these two probabilities must be always 1. So this is full information, and the only unknown is the parameter p. If you can fill this number, then you know everything about the distribution. It's obvious. This is the simplest possible statistical model, right? So, but we are going to spend one whole chapter under this assumption. So, as I said, assumptions are basically binary, right? And also another assumption is that we are going to parameterize the probability of success, right? And we are going to call that P. And then there is a name for this. Then under these assumptions, the random variable is called a binary or Bernoulli distribution with parameter P. So Bernoulli is a statistician many centuries ago who studied this distribution maybe. And mathematically we are going to denote this statement in this way. A random variable x follows binary distribution with parameter p, or Bernoulli distribution with parameter p, right? So pretty simple. Okay, then before studying the properties of the Bernoulli distribution, let me make a few comments. So I said P is a parameter, right? So parameter is a few numbers, a few measures that can fully characterize the distribution of a random variable, right? By the way, but what's important here is the random variable must satisfy a certain assumptions. So you have to specify the assumption and the parameter, then you know everything, right? So here, when I say binary, this indicates these assumptions, right? So when I say x follows binary, that means x satisfies these assumptions. And then the only unknown is p. The parameter is the only unknown part of this distribution. So that is how you understand parametric distribution. So the simplest example was binary distribution, but you can extend you can change the assumptions, and you can think about different types of parametric distributions like normal distribution and Poisson distribution, gamma distribution. But of course, different distributions will use different assumptions, and then their parameters will be different. They are going to parameterize different in different ways. So one distribution is not compatible with another distribution in general. Okay. So as I said, there are more examples of parametric distribution, but I'm not going to cover them in this course. But we are going to study two most important parametric distributions today. Okay, let me start from another simplest possible example, coin toss. From a coin toss, I'm going to call heads as 1, as success, tails as failure or 0, right? So success is heads, failure is tails. And in 5 experiments, I observed these numbers, these outcomes, like heads, tails, tails. So then, simple. Calculate the probability of heads from the observations. It is too simple, so I'm going to show you the answer. The answer is 40% because out of 5 observations, 2 of them are heads, so that is the probability based on the data. Now then, I will ask you what is the mean of the observations. There are 5 numbers, so you should be able to calculate the average. Try that. again, when you calculate, it is simple. Calculating the mean is adding all 5 numbers and dividing by 5. And if you add these 5 numbers, it's easily 2. You can see that 2 divided by 5, which is again 0.4. The mean is 0.4, right? So what I want you to say here is calculation is too easy, but what I want you to note is that the mean equals this probability. These two questions had the same answer. It is not by coincidence. It is a property of a binary random variable. So always, for a binary random variable, always the probability of success equals the mean. Okay, let me explain why. So it's because we encoded the outcomes as zeros and ones, right? So when you count number of ones, so in here, when I ask you what is the probability of heads, which means probability of ones observing ones, then you are counting 1, right? 1, 2. There are 2 ones, 2 successes. That process is mathematically equivalent to adding those 5 numbers, adding ones and zeros. When you add zeros and ones, then the result is equal to the number of ones. If you have a number of ones, that's their sum, right? So you have to observe this. Number of successes equals the summation of those ones and zeros, right? Summation equals sum of the observations must equal to the number of 1. And number of successes is number of ones by definition. So as a result, they should always be the same, right? So probability and expectation in their process, basically what you are doing is counting ones, counting successes. So they are always the same. And then, why is it important? Well, because I am going to interpret the mean as a probability. So think about this. We are considering coin flip. 1 is heads, 0 is tails. By the way, 0 and 1 doesn't mean anything. We are just encoding them, encoding 2 outcomes as zeros and ones. So there is nothing in between them. Like 0.4 has no meaning. 0 has no meaning. 1 has no meaning. There is nothing in between them. It's just heads or tails. So 0.4 is not the possible outcome, right? Like when you compare this with, like for example, if you think about a typical numerical variable, say, what is the expected number of, like say, stock return next year? Expected number of expected GDP growth rate. So then, if you have any number, like say, expected stock return tomorrow is say 10%, then you know what it means. Like 9.9%, 9.9, 10, or any number is a possible outcome. And kind of easy to understand what it means. But here, in this example, numbers are not numbers. Numbers are just labels, names for the outcomes. Therefore, 0.4 has no meaning as a number. Instead, because now we know that the expectation equals the probability of success, I recommend you to interpret this 0.4, the mean, the mean, the expectation is better interpreted as a probability, right? So interpret 0.4 not as an average, but as a probability of heads. That would be nice. That would be better. However, mathematically, still it is a mean. So what is good is what's good about this is you can apply all the properties and the methods that are applicable to mean. So if you are interested in the probability, that's what we are like what we parameterize. So you'd like to know the probability, but we know the probability equals to the mean. Therefore, you cannot use statistical methods for mean when you infer about the probability. So by this property, equivalence of mean and property of probability of success, you can enjoy many nice properties later. Okay, so this is the end of the first video. So in the next video, I'm going to change the example a little and we'll extend the distribution model, the statistical model. Thank you for watching. See you later.